So if you're doing a plug-in for number one, I would love to see parentheses around -12, and that's going to ensure that we do a negative times a negative is a positive, and that your negative sign doesn't get lost. So that would be positive 144 times negative 17. So who did that? Who's got that number? Seth?
I got -2,443.
Alright, so you have 5, so that's a negative.
I thought that's the final part. I had -2,448. I thought you meant the final one.
And so the final result, negative 2,443. Great job. So again, when I plug in a variable and there's an exponent used, I like to use parentheses around the negative, particularly when you're using a calculator. It's a lot more accurate if you get your parentheses in there. I wonder what this one's going to be. Okay, I can wait for sure. Question. Is this the same thing we did yesterday? Darn it. A repeat problem on our hands. Remember we talked about reducing this fraction? Is it looking familiar to anybody? Same problem. How unfortunate. So it's 60. So I did step by step. I did 12. I did 3 times 4 first. And so that would be -12 times -5. And that's multiplication there. 12 times 5 is 60. You got 2 negative signs, making it come out positive. So what was the reduced form? Go ahead. Do I have a mistake? I forget what you're talking about. Okay. So 3. Yep. Okay. And in your calculator, you're using this button, not the squared button, but the up arrow. That'll get you 81 as well. Go ahead, Torian. What's the reduced fraction?
-4739.
Yep. And then someone offered a mixed number yesterday as well. Go ahead. Sometimes we repeat problems, and you know what? Research actually shows it's good for you to see problems twice. This is the answer I prefer here. Okay, get out your homework, please. So, again, this is mostly just defining words, defining properties. Does anybody know what the natural numbers are? If I said, tell me the first 4 natural numbers, go for it. 1, 2, 3, 4. And where do they go? They go to infinity. These are called counting numbers. It's natural because you can count things in front of you. These are the numbers that you first learn when you're 2 years old. The natural numbers. Parents will naturally teach their kids to start counting at 1 and go in order. Next is whole numbers. Whole numbers is a bit more advanced. The same things, the natural numbers and zero. So if you have a set of numbers and it starts at zero, you call them whole numbers. Integers are whole numbers and they're what? Anybody? What do you think was there? Opposites, or they're negatives, yeah. So integers will go on both sides of the number line. Left and right to infinity, just no decimals. Rational numbers, any number that can be written in the form of a over b, meaning a fraction, where a and b are integers. So if you put an integer over an integer, like 3 over 4, that's no longer an integer, it's a rational number. And it could be in decimal form. So in decimal form, it's a terminating decimal. What does the word terminate mean? It stops. It's a decimal that like definitely ends, or a repeating decimal. So you irrational numbers in decimal form do not terminate or repeat. They never end and they never repeat. They go on forever with no pattern, so we call them irrational. You're just acting irrational right now, going on like that forever without any pattern. Let's hear it. This is where pi falls into play. What's that mean? Yes. I don't know how to use gaslighting in a sentence, but I'll think about that. Yes. Those numbers, they're just irrational. I see I'm personifying them more than anything. All right, the other really common irrational number is like any number that doesn't square root, like any non-perfect square. Like for instance, what's the square root of 5? It's 2.0 something, but it goes on forever and there is no pattern, it doesn't repeat. In fact, any number that's not a perfect square, if you put it under square root bar, is considered irrational. Real numbers are all rational and irrational numbers. Okay, so here's some examples. Okay. So I'm going to label this diagram. If you hate this diagram, fine, but we're going to do it anyway. So this is the rational side, and this is the irrational side. Okay, so in our innermost little rectangle, we'll put the natural numbers. This will just be like a little review. We're going to rewrite it. And then if you're broader than natural numbers, you also have whole numbers. And that would be every natural number and 0. Let's put another way a whole number could be represented. Maybe you see something like 12 over 4. It's a fraction, but it's still a whole number, right? Because it reduces to 3. So make sure you consider numbers in like their simplest form. Or maybe you see like the square root of 100. The square root of 100 is 10, so that's still a whole number. Next is your integers. Really just rewriting. So how could an integer, like maybe negative 25 over 5 or negative square root of 49, that's an integer. And then last, who's got an example of a repeating decimal in fraction form? Anybody? Go ahead. 1/3 is a rational number. It's like 0.33 forever. Any other fractions that would be like a terminating decimal? Anybody tell me a fraction that if you put it in decimal form, it's real simple to the point? All right. 1/4, because that's 0.25. That's rational. Irrational, like we said before, is pi. Any number that doesn't actually square root well, if you just don't naturally know the square root of it, it's probably irrational. For now. All right, so let's do these examples now. There's not really enough room on your paper. I don't know how small you can write, but okay, list every classification, every set of numbers that 15 falls into. You guys go ahead and do all of these in your groups. Try to figure them out.
So I guess it's rational.
We just like write the letter in the box that like could be in the graph.
Yeah, you can use an abbreviation. If you fully understand your abbreviations, you can use them.
I don't understand the difference. So
Those are all numbers.
yeah, it's in a one. It's none of it. Yeah, it's irrational. That's why all the boxes are like in the rational.
Even in your like assignment tonight, you can use abbreviations.
For number C and D, what's the number? Not actually.
Oh. Alright, so I have answers on the screen. I want you to list everything that every category they fall into. So 15 can be classified as a real number, a rational number, an integer, a whole number, and a natural number. The only thing 15 is not is irrational. B, if you need to put it in your calculator and think about the decimal form, you can. 1.2. It's a terminating decimal, so we call it rational. And it's a real number. These are the only two that you could list for letter B. Same thing for C. If it had a dot, 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 it would go on forever, but it doesn't. I don't think that one actually. And D is irrational. All of these are real numbers. Maybe I should say what a not real number is. Who knows what a not real number is? Did somebody say I? Okay, something that's not real would be a negative square root. Right, you can't square root a negative, not a real number. Like in algebra 1 when you did quadratic formula, you would have said no solution if you square root a negative. This is not a real number. This is not a real number. It's actually called imaginary. We'll spend like weeks on it, but you would write it as 8. I for imaginary. And the reason is, it's not negative 8, right? Because negative 8 squared is a positive 64. So what's the square root of a negative? Doesn't even compute. So we say it's imaginary. Anyway, all of these are real numbers, so that's why I put real number for everything. Yes. Well, let me show you what I would have wanted to see if I was going to deem it irrational. I'd like to see if this is an actual fraction. This ... would indicate that it goes on forever without repeating. As I see it right now, it actually does end. Okay, there's no symbol there showing me that that goes on forever. Another indication that a number has gone on forever, but it has been rounded, would be these squiggly equal sign. That means approximate. This means this number has been rounded here. So that I would be tempted to call irrational, but the way it looks, it's a decimal that ends. There's no ... with it. Okay, let's do those last four on the bottom. Now you have an idea of what's going on. List all the sets that they go into.
No, rational because it's 3. The answer is 3. So it's like the same 16. Because yeah, because when it's 3, so it's integer, whole, and natural. It's like a decimal that goes on. It's just yeah. 12. That's
Check it out. Anybody try to square root 12 and just see it? Like, I'm wondering if your calculators go around it, like how many places it fills up with decimals. If you square root 12, I mean, you have to put your calculator in classic mode, but this calculator gave me 9 decimal places. That must be the setting it's on, because it could just fill up forever. That's a really good mode. This is the mode we wanted. Okay, are we ready to flip to the back? Alright, so you've heard those classifications of numbers. Now here's some properties that you've heard. Anybody know what commutative property means? Go ahead. Yeah, it switches the position of terms. My letters are kind of smushed in there. That says switches. So if you've ever heard anybody talk about their commute to work, does any of your parents commute to St. Pete for work every day or commute to Tampa? Anybody commute to Sarasota? Anybody go to St. Pete, honestly? Tampa? No? Your parents for work.
Yeah.
Like every day over the bridge. They have a long commute. People complain, oh, my commute's 2 hours. My commute's too long. And it is terrible to commute a long way to work. So, anyway, when you commute, you're moving from home to work or work to home. And in math, when a number commutes, it's changing positions. So I'll give you an example. Okay, what from left to right, which numbers switched positions here? Go ahead. And why did they switch? Yeah, this is better. And we do this mental math anyway. If you had to add these numbers together, you would combine the 17 and the 3, make it 20, and then that's 29. It's a lot better than doing this math. So that's an example of a commute, the 3 switched. And that's the same for multiplication. And you can switch if it's all multiplication, you can put those in any order you want to. All right, anybody remember what associative property refers to? Go ahead. Moving grouping symbols. Yeah. So what helps me remember this one is it's called the associative property. If you've ever heard on TV, I'm sure your parents would never say this. I don't like who you're associating with. You know, a parent talking to a kid. The group that you're associating with this year is not that great. Pick a new group to associate. Who are you choosing to associate yourself with every day? So that's your parents complaining about your group of friends, right? So let's look at moving grouping symbols. Your parents have never said that. Fail. I feel like I just woke up again.
Now I gotta answer it.
Is that your alarm? You don't have to answer that. Okay, see how the grouping symbols switched? Because 5 would rather be grouped with 15. They go better together. They make a good team. 5 doesn't belong with 14. 14 is a bad example. 5 is going to change its group and associate with 15. Changing grouping symbols. All right. In identity properties, the value will not change in the math. Okay, this is just like in health class, you learn about your own identity and staying true to your identity. You go to high school and you don't sell out. You stay true to your own silly self and you maintain that identity. Well, that's true in some math problems. Like in addition, 5 can go and become a part of this equation, but 5 stays 5. Stays true to its identity. This is an identity property. 5 was always 5, and it was added to 0, but did 5 change? No. 5 was no sellout. It kept its identity. The same thing happened to 5 in a multiplication problem. 5 was multiplied by 1, but it stayed 5. 5 does not change its identity. That's an identity property. The value does not change. So in addition, it's always adding 0. In multiplication, it's always times 1. Inverse properties show canceling out. Something such as 3 plus a negative 3 cancels, gone. In fractions, it's like reciprocals. If you multiply the reciprocal, you cancel to be 1. That's an inverse property. Because that's how you, in multiplication, how you stay the same. Is there any number that I can multiply 5 by and 5 stays 5? Only 1. Only 1. So that is what's is highlighted an important point. In the identity property, you're adding 0, but you're multiplying 1. They look different. Distributive property is multiplying one number into a group. You guys are all very good at that. We'll just do 6 times x plus 4. And that's the same in addition and multiplication. Okay, go ahead in your groups and try to name the properties 1, 2, and 3.
Reverse associative. Associative. Yeah, but until you're moving numbers closer to like 7 plus 23, so it's better to understand that instead of 16 plus 7.